Our next presenter is Sydney Taylor. Sydney Taylor is a Johnson Space Center Graduate Pathways intern and a 2016 NASA Space Technology Research Fellow. She's studying aerospace engineering at the Arizona State University and will graduate in December 2020. Her PhD research is focused on variable emissivity coatings for spacecraft passive thermal control. Good morning and welcome, Sydney.
Good morning. Thank you very much for the introduction. Can you guys hear me okay?
I hear you loud and clear.
All right, awesome. So thank you everyone for attending my presentation on the model validation for beam with stowage. So today we'll be talking about the background and history for beam. Then we'll discuss the on-orbit flight data and model validation cases that we looked at. Then we'll discuss the model results from those validation cases. And then we'll discuss some results from the low IMV flow model that we also did. And then finally, I'll discuss the results and conclusions. So just as a background for beam, so beam, which is shown in this bottom gear, if you look at my pointer. So the Bigelow Expandable Activity Module, or beam, is a collaboration between NASA and Bigelow Aerospace. So it was birthed to the ISS Node 3 aft port on April 2016. And then in this bottom set of figures here, you can see how it was birthed and then expanded to its expanded configuration. So originally, beam was a 2-year mission to validate the overall performance and capability of expandable habitats. So it was kind of like a tech demonstration mission. So why we were interested in expandable habitats is because they can offer advantages such as low launch mass, high volume to habitable ratios, lots of benefits for, say, radiation shielding, etc. So one other interesting feature of the beam is that it's configured with these wired temperature sensors, or WTS. So if we look at the top right-hand figure, you can see these yellow dots represent where the WTS are. And that's important because it'll provide us with the flight data that we need to validate our model. So some additional history for the beam is that there was one flow case, low flow case, that was observed starting in August 2017. So there was around 66 CFM reading on August the 24th, and then that decreased further to 45 CFM on September 21st. So the nominal CFM rate, or the flow rate for the IMV for the beam, is 120. So this represented a pretty considerable reduction in flow. So the cause for this low IMV flow rate was determined to be a blockage of the Node 3 aft port fan. So that was fixed, and then the flow rate returned to nominal. So some other additional history facts for beam is that they converted the WTS from wireless sensors to wired sensors, and they also placed these cargo bags, which they pre-positioned on November 21st, 2017. And then, so you can see that in the lower right-hand figure, the white things here, the cargo bags, they're not filled yet, but they're pre-positioned. And then this is a duct that takes the IMV air from Node 3 and then brings it from the forward bulkhead here to the aft bulkhead here. So that's how we're able to provide the thermal control for beam. So that the cargo bags were filled on January 24th, 2019. And then after the bags were filled, the temperatures in beam were monitored for an additional 60 days after the stowage was completed. So the motivation behind trying to put stowage in beam was that the ISS, as probably many of you know, has significant limitations with stowage. And after the tech demonstration mission was completed, beam looked like a great option to stow flight hardware and increase the stowage capacity of ISS. So some previous studies were done to evaluate whether stowage could be added to the beam without degrading the thermal performance. So the main consideration there was that condensation could form in the beam, and that would definitely degrade the thermal performance. So what we wanted to check is, would the temperatures in the beam get too low, and then that would cause the condensation to form. So a study was done to evaluate that. And then in January 2019, the approved 109 stowage configuration. So previous studies looked at which configurations would kind of provide the least impact to the thermal performance. So you can see on the right-hand side, this is a stowage configuration that was approved. So you've got basically 3 types of bags, and they're configured in this setup that you see here. So as I mentioned before, the WTS data, so the sensor data, was monitored for 60 days to confirm that the stowage had minimal impact. But 2 important things to note is that the beam did not experience extreme conditions, and it also didn't experience reduced flow rate during those periods. So those were 2 still unanswered questions for the beam. So that takes us to this study. So the objective in this study was to, 1, correlate the model and be able to show that, yes, it now agrees with the flight data. And then 2 was also to try to determine what the impact would be for the lower flow rates for the beam. So here's an overview of last year. So as I mentioned before, the stowage was completed in 2019. And then this chart goes all the way to the end of 2019. So the WTS temperature sensor data is reported on a quarterly basis. So you have the red, which represents that aft bulkhead that I pointed out earlier. Then you have the blue, which represents the forward bulkhead. And then you also have black, which represents the air barrier of the beam. So the model, we validated that with 3 low temperature events, which I'll talk about on the following slides, that occurred in 2019. And that was after we put in the approved 109 CTV stowage. So the first case that we looked at was July 2019. So that case was of interest to us because it represented the all-time lowest flight temperatures that were observed on beam. So that low temperature that was observed resulted from 2 factors. One was the ISS attitude, and the second was that July is the annual solar minimum, so you have the smallest amount of solar flux. So the ISS attitude, why that ended up making the beam so cold, was that there was a maneuver from the plus XVV to minus XVV attitude. And then that also had a high solar beta angle, and that exposed the beam to the full ISS shadow. So that's what caused it to get very cold. One thing to note is that there was still a nominal IMV flow rating of 109 CFM. So anywhere between 90 and 120 is considered nominal, because 90 is where they replace the filters and where they've kind of earmarked as a, this is where we no longer consider our flow to be nominal. So then one thing to note is that the minimum temperature that was observed in the flight data was 14 C. So if you look at most of the data, kind of 20 C is more normal, kind of for the aft bulkhead, which is the coldest part of the beam. So that represented a considerable decrease in temperature. So the next case that we looked at was October 2019. And this case was of interest because it was the only low flow rate case recorded after stowage. So we had a reading of 50 CFM IMV flow, and that was on October 21st. And we hypothesized that the lower flow could have began as early as September 2019. So again, the min flight temperature for the October case was very close to the all-time low of 14 observed for the July case. So this marked another low temperature event that could be of concern for forming condensation in the beam. And then the final case that we looked at was December 2019. So that's of interest because it's an annually recurring cold case for beam since 2016. So since 2016, there's a cooling trend that's been observed. So each year, the minimum kind of goes a little bit lower. So that's also concerning. And this minimum annual cold case occurs due to the solar beta angle approaching the -75 minimum, which will give you the coldest temperature. And then there was also a nominal IMV flow rate of 120 CFM. And then the min temperature was 15 degrees Celsius, which is also very close to the other low temperature events that we've talked about. So those were the 3 model validation cases that we looked at. So the last thing I'll do here is just compare with some of the historic flight data, just to put it in context of before stowage was added and after stowage was added. So if we look at similar times of year and beta angle, for the October 2019 case, which is these blue boxes, then we notice that you don't see the minimum that you start to see in the 2019 case. So that case was somewhat of an anomaly due to the low flow rate. Whereas in the December 2019 case, we observe in the purple here, you have an annually recurring cold case that kind of just gets lower and lower. in terms of temperature, and that's been observed since 2016. So that's kind of the flight data history of the beam. So the next thing I'll talk about is the model overview. So to do this work, we were working with the ISS V7 Rev1 beam Rev6 model. And there's many parameters that you need to change to be able to perform date-dependent analysis. So we performed analyses for each of the dates that I mentioned previously. And then the other thing that we do is we adjust the visiting vehicle configurations for each case. So that'll be things like the Soyuz or the Dragon or Cygnus. So we adjust where those are depending on if they were or were not visiting during that date. So in the bottom left, we can see this is the entire ISS model. And then this arrow is pointing to beams. As you can see, it's very small compared to the rest of the ISS. And then on the right-hand side, we have a figure of the beam model, and you can see the flow paths, for the air passages for the thermal control. So here I just wanted to overview what parameters we were changing to be able to do this analysis. So some of them are self-explanatory, like we have the beta angle, and then we have yaw pitch roll, and then we have the solar constant, OLR, and albedo. Then you have these P charges and S charges, as we've been calling them. So the TRRJ, that's the thermal radiator rotary joint, and that's shown in this picture here. You can see where it's located on the ISS. So P stands for port and S stands for starboard. And we basically will adjust the model parameters to describe what configuration the ISS was in on the dates that we're looking at. So for an example, we have GMT 200, which is our July 2019 case. So we'll put in the data that we receive from FOD accordingly to be able to represent that case. And then similarly with the SARJ, or the solar array alpha rotary joints, we also put in what configuration they were in. So in all of the cases we looked at, those were in auto track mode. So you can see kind of where those are located in this figure. So then the next thing that we also looked at was the visiting vehicles. So for each of the days, we tracked which vehicles were there and which node they were located at. So in some cases you had the Soyuz, so July you had the Soyuz, so we had to place it accordingly. And then we had the Dragon in all of the days that we looked at, and then Cygnus 2 of the days that we placed it. So on the bottom left-hand side here, you can see where those vehicles would be placed if they were present during the days that we're looking at. So then the next thing that we did is we went ahead and ran the cases. So I wanted to include just a sample model output that we had. So we probably generated many more of these, maybe 50. So that would be for the GMT, or the day that we were looking at. So this is December. We also did for the nominal flow rates. And then for July, we also did low flow rate cases. So that's what this denotes. And then another factor that I'll talk about in the next slide, which is some degraded flow cases that we looked at. And then in some cases, we also looked at different attitudes, so say -4 yaw or +4 yaw, for an example. So this is a transient case that runs from anywhere between 35 to 70 hours. It depends on the flow rate. That we generally found that the higher the flow rate, the sooner it would take to kind of reach a steady state scenario, whereas if it was a lower flow rate, it typically took longer to reach steady state. But anyway, we would run it for 35 to 70 hours to be able to observe the steady state minimum temperature. So in this case, it was 14 C, as I mentioned, for the December 2019 case. And then the other thing we do is we select the coldest sensor location. So that usually occurs at the aft bulkhead. There's a particular sensor on the aft bulkhead that reads the lowest temperature. So we selected the coldest one. So that way we can make an evaluation of what the coldest temperature was in the beam, and that would help to inform some flight rule updates. So this is a summary of the model validation cases that we did. So you'll see that these are the different dates. We looked at July, we looked at October. You'll notice that there's two things for October. The reason for this is that the CFD parameters that we had them for 30, 60, 90, and 120. So since our CFM reading for the October case was 50 CFM, we kind of ran both the 30 and the 60 case, and we expected to see that the results from that would bound our flight data. So you'll notice here that We ran a baseline, and then we ran what we're calling a degraded case. So what happened with the degraded case is that at first the model and the flight data weren't lining up very well. So there was a series of different factors that were examined to see if we could adjust those to get better agreement. And the factor that we ended up finding was if we degrade the heat transfer coefficients, or HTCs, on the aft bulkhead by 10%, we found that we got very good agreement between model results and the flight data. So you can see here, there's less than 1 degree difference. So like for an example, 14.4 here versus 14.3 here. So they're very close. So once we found that, we ran that for all of the cases that we were examining. We found good agreement. And we also found that in the case of our October case, our model results did bound our flight data. So we were pleased to see that. So after we got these results, we were confident that the model was validated for the beamless stowage. So this is also just a summary of another case that we looked at, which was in 2017. And that was another low flow case before the stowage was added. And we found that in that case, the non-degraded model results were in good agreement with the flight data. So what was interesting to us was in the low flow case, we found that the flow rate did have a significant impact on the flight man data. Whereas we found that in the 2017 case, we did not need to degrade that flow rate. So that was one interesting thing that we learned. So having to degrade by the 10% was definitely something that arose after we added the stowage. So some other factors we examined, as I mentioned, we examined quite a few different factors to try and figure out why we weren't getting a good agreement between the beam model and the flight data. So some things that were looked at was adding more isolation from the beam debris shield, also looking at the couplings to the soft goods attachment ring, looking at potential shading effects from visiting vehicles. We found that these above factors didn't really have a significant effect on the beam minimum temperatures, so less than half a degree. So those were discarded. Those changes to the model were discarded because they weren't explaining the difference that we were seeing between the flight data and the model results. So in terms of degrading the HTC heat transfer coefficients on the aft bulkhead, we did look at 0.1, 0.2, and 0.3 as factors to degrade by, and we found that the 0.1 provided the best agreement with the flight data. So the final thing that we looked at was also some low flow rate cases. So as I mentioned, we only really had one example of low flow after the stowage was completed, which was that October case. What we wanted to see now is if you had kind of the worst environment, so that was the July environment that I mentioned earlier, and then you had reduced flow rate, what would be your minimum temperature that you would get on your beams? So that set of results could help provide a flight rule update recommendation. So that's what's in this table. So we looked at 30, 60, 90, and we also looked at different IMV inlet temperatures. So normally it's set to 72. However, some crews prefer 68, so that is also a possibility. So we looked at that as well. So that helped us generate some charts to say if you have this flow rate and this IMV, this is what your minimum temperature is going to be in the beam. So now you can make some updates to the dew point flight rules for the beam. So the other thing that we looked at that I didn't put in these charts was we also looked at the auto track cases, and we looked at that for 72 Fahrenheit IMV, and we looked at that with nominal flow rate and the worst case flow rate, and we were able to provide some recommendations for that as well. So the conclusions from the study were that we were able to validate the model, and we got good agreement with the flight data, less than 1 degree C difference, by adding this 0.1 degradation factor to the shear heat transfer coefficient for the aft bulkhead. So we have our beam model is correlated for the stowage addition, and then we were confident that we also partially correlated the model for low IMV flow since we only have one case to go by for the flight data. That's a partial correlation. And then we were also able to use the low flow model results to provide some flight rule update recommendations. So these are some references from the presentation. If anyone wants to check out some information on beam or on some of the previous studies, then these are some great references. And that concludes my presentation. I'd be happy to take any questions.
Well, thank you, Sydney, for your presentation. Let's go over to Warren and see if any questions have come across the chat yet. I seem to have lost my, oh, there we go. I had to reestablish my link with the stream. It timed out or something. Okay. There's a delay between this and the stream, so
okay.
They may be just hearing you finishing up your presentation. So we'll give it a minute or so here at minimum and double check the chat. So just stand by for questions.
Okay.
Hey, Sydney, this is Warren. So I have a question. What's the suspected cause for the degradation in the heat transfer coefficients?
That's a good question. So I know that they installed some netting, and I think there was some concern that maybe that might have affected it. Some netting to like hold the cargo bags.
Okay, thank you. So we've got a question here. What's the prediction for the real life cause? What's the prediction for the real life cause of the degradation factor on the heat transfer coefficient?
Oh, I didn't quite hear you.
This might be similar to the question that I asked, but what's the prediction for the real life cause of the 0.1 degradation factor on the heat transfer coefficient?
Right, so that's applied to the aft bulkhead. So there would have to be some change that was made between, around the time that the cargo was stowed, potentially, that could have caused that. So we're still not sure exactly what the cause for that is. As I mentioned before, there could be that netting, or it could be some other factor.
Okay, thank you. We've got another question in. How much damage would condensation cause in beam?
Well, I think the main concern is just it would degrade the thermal performance for the beam. So now you have an interaction with water on the surface that you didn't expect to have.
Okay, yep. Did you look into how much the condensation would affect the results of your analysis?
So that's not something I've looked into. I'm relatively new to this project. So that might have been something that another person has looked at, or, that we can also suggest that someone looks at, but that's a very good point.
Okay, thank you.